Okay, so in this video we're going to start talking about the concept of the electric field, which is going to be a very important concept for the rest of this unit. Okay, so far we've been looking at the Coulomb's law, which allows us to calculate the electrical force between 2-point charges. And so we know, of course, if we have at least 2-point charges, there's some type of electrical force between them. Notice that this electrical force exists even though that the two charges are not physically touching. And so I asked two questions here. Number one, what other force have we seen that involves no physical contact? And two, how is that force, or how are these forces transmitted between the objects? In this case, the two charges. How is the electrical force transmitted? What is the mechanism for that? And when I say mechanism, what I mean is if I push on a box and I write that down as an applied force on an FBD, I know exactly where the force came from. It came from my hand touching the box. But if you have just 2-point charges out there with nothing connecting them, no physical contact between them, it's a reasonable question to ask, what is the mechanism by which that force is transmitted? Now, the other force we've seen that has a similar type of property is the gravitational force. And so, going back to the time of Newton, there was this question being asked, how are these forces being transmitted? Whether they're electrical forces or magnetic forces or even gravitational forces with no physical contact. And one of the ideas that came about is the concept of the field. And so, if we make the analogy to the gravitational field and then come back to the electrical field, hopefully it will make more sense. Now, the concept of the field, by the way, is kind of an abstract type of thing, and so I'm going to do my very best to explain it. Please feel free to ask questions if you have any questions. And so, we're going to start by talking about the gravitational field, and then switch back over to the electrical field, because gravity is something that maybe is a little bit more relatable to people. Okay, so first of all, I should tell you what I mean by a field. When I say a field, I basically mean, in the mathematical sense, a field is some scalar or some vector which has a single value at every single point in space. Okay, so just to give you an example of that, you could have a temperature field. At every single point in space in the universe, there is one and only one temperature at that point in space. Okay, now, of course, you can have different units of temperature, whatever, but you can't have two temperatures at a single point in space. That doesn't make any sense. You can also have things like vector fields, and gravity is an example of that, where you have a single defined vector quantity at every single point in space. And I don't know if all of you are going to understand what I'm about to say, but when you hear me say a field has a single value at every point in space, hopefully at least some of you think of the concept of a function, because in mathematics a function basically has one single y value for every value of x. That's what a function is. And so you can kind of think of a field as like an extension of that to physical space. So anyway, talking about the gravitational field. An object is located in a gravitational field if it experiences a gravitational force at that location in space. Okay, so everywhere in the universe, at every point in space, there is a single value for the gravitational field at every point in space. Now, the way we define that is, well, first we give it a symbol. Okay, and so the symbol for gravitational field strength is a lowercase g. And the gravitational field strength at a single point in space is defined in a very specific way. Okay, the gravitational field strength, little g, is defined as the gravitational force that object is experiencing at that point in space divided by the mass of the object. Okay, and so if I just pick any point in space in the universe, if I take an object out of my pocket, it doesn't matter what it is. If I put it at that point in space, measure the gravitational force, divide by the mass, that quantity which I just computed, that is the definition of the gravitational field strength at that location in space. Okay, at least the magnitude. Of course, the direction for gravity is an attractive force, and so the direction of that vector would depend on some things. But that's how gravitational field strength is defined. When you think of gravity like close to the surface of a planet, you think, falling objects, and so the direction of the gravitational field close to the surface of a planet would just be pointing down. It would be a vector whose magnitude is given by this equation. Okay, the gravitational force at that point in space divided by the mass of whatever object you care about, and the direction would be, down, basically. Okay, and so that's how gravitational field strength is defined. Just to show you a visual representation of this, here we have the gravitational field shown for two different situations. On the left we see close to a planet, and on the right we see close to the surface of a planet. Now, once you get out into space and you start getting farther away from the objects you're talking about, we treat gravity a little differently, because then we think more of the force of gravity in terms of being, g m1 m2 over r squared, which is Newton's law of gravitation. Whereas close to the surface of a planet, we think more along the lines of the force of gravity is mg, which is more of a constant value. And so that's why these two situations look different. But the point I'm getting at is this. If I take, let's say, a rock out of my pocket, and I put it up in the air, and I let it go, it's very obviously going to experience a gravitational force. Now, of course, even if I don't let it go, it's still going to experience a gravitational force. Okay, the concept of the field is this. If I don't put the rock there at that point in space, there is still something happening at that point in space, whereby when I do put the rock there, it immediately knows to fall. Okay, so in other words, whether or not I take the rock out of my pocket and hold it out in my hand, there's still some type of gravitational field that exists independent of any object that I put there. And now, in the case of the Earth, that gravitational field is produced by the mass of the Earth. And generally speaking, mass produces gravitational fields. Okay, so any mass in the universe creates its own gravitational field, and that gravitational field affects all other objects in the universe that have mass. Okay, so that is basically kind of the idea behind the gravitational field. Okay, there's something happening in space. If I, take the rock out of my pocket and I hold it out, I can calculate the gravitational field strength there. It's Fg over little g, or it's the force of gravity divided by the mass of the rock. But even if I don't put the rock there, there's still something there, invisible to my eyes. I can't see it. I can detect it, but I can only detect it if I put a mass there and then measure the force. Okay, so this idea of the gravitational field is kind of an abstract thing. It's not something we can see. It's just kind of an idea to explain the fact that if I put the rock out, if I let my hand open and the rock starts to fall, the rock instantaneously begins to fall. And so either the force of gravity acts instantaneously fast, or there was already something happening in that space to begin with, and when I let the rock go, it just kind of acted on that invisible field that already existed. And going back to Newton, both of those ideas were thought of as possibilities. Nowadays, we think more in terms of fields as being the correct view of the universe, rather than the idea of instantaneous, what they called back in the day of Newton, action at a distance, where if you think about the force of gravity, if you have let's say two planets like 1,000 light years apart, if one of them just blows up and disappears, the other one would instantaneously feel the gravitational effects. Okay, in real life that doesn't actually happen, because action at a distance is not really a thing. The gravitational field is a thing, and it takes time. It would take time in my hypothetical scenario. By the way, if a planet ever blows up, that would be pretty crazy. But it would take some finite amount of time. If one planet were to blow up, it would take a finite amount of time for that information to be transmitted through the gravitational field to the other planet. And yeah, so action at a distance, not a thing. Gravitational field is a thing, and it exists whether or not you put a mass out there to measure it. Okay, so hopefully that didn't completely confuse you, and then we can carry this analogy over to the gravitational field. carry this analogy over to the electrical field. Okay, so let's see, I talked about that already to explain how force is transmitted at a distance. I already talked about what a field is. So the analogy for the electrical field, rather than it being mass that creates an electrical field, in the case of the electrical field, it is charge. And so any object that has charge creates an electric field that surrounds the space around it. And then if you were to put a second charge out there, that second charge would feel a force, given by Coulomb's law, but it would feel a force because it is existing in the electrical field of the first charge that you started with. Okay, so all charges produce an electrical field, and that electrical field interacts with all other charges. Now, in the case of the gravitational field, we define the gravitational field, little g, as basically the force of gravity, the gravitational force a mass would experience, divided by the magnitude of that mass. Okay, the electrical field is defined in a very analogous way. And I realize, by the way, this is a very abstract thing I'm talking about, and so I apologize if this is confusing to you. It is somewhat expected to be very confusing because it is a very abstract type of thing. And in a second, I'll try to show you some simulations of what electric fields kind of look like, so you can try to visualize what I'm talking about. But it's kind of difficult to explain in words. But anyway, getting back to how the electrical field is defined. Here's how the electrical field is defined. Let's say I go out into space and I take a charge out of my pocket and I put the charge at some point in space, and lo and behold, there is an electrical force on that charge. Why is there an electrical force? Because some other charge somewhere created an electrical field. Whatever. Okay. Maybe a whole mess of charges created an electrical field. Doesn't matter. Okay. The point is the electrical field at that one point in space is defined as the electrical force felt by that charge divided by the magnitude of that charge. Notice I'm using a capital E. That is the symbol for electric field. Sometimes they'll call this electric field strength, but electric field. Okay, so capital E is the symbol for electrical field, just like lowercase g is the symbol for gravitational field strength. Okay, so you have electrical field strength and gravitational field strength. And notice they're defined in very similar ways. Okay, electrical field strength is defined as the electrical force per unit charge at a point in space. Okay, so go anywhere in the universe, take a charge out of my pocket, doesn't really matter how big the charge is, put it out there, measure the force on it, divide by the size of the charge, and that value is the electrical field strength at that point. Keep in mind, something that confuses some people when thinking about this concept is the charge I'm talking about that you take out of your pocket and you're basically using to measure the electrical field. This little q is often called the test charge, and it's a test charge in the sense that you're using it to define the electric field at that point in space. It doesn't matter what the charge is exactly, you're just using it to define the electric field strength at that point in space. But some people will get confused, and rightly so, because they'll say, well, doesn't that test charge that you're taking out of your pocket, doesn't that have its own electric field? And the answer is yes, of course it does. And so we're going to assume basically that the charge that I'm taking out of my pocket does have its own electrical field, but its own electrical field doesn't affect itself, if that makes any sense. A charged particle cannot affect itself. It can affect other charged particles, but it can't affect itself. And so yes, the test charge, technically speaking, would have its own electrical field, but we're kind of ignoring that for the sake of defining electrical field strength. Okay, so when I say I take a charge out of my pocket, I put it in space, I measure the force, I divide by the charge, that gives me the electrical field strength. I'm assuming that my test charge is so small that it didn't actually change the electrical field in the space where I'm measuring it. Okay, so please pause there add some of that to your notes, and I will show you one or two simulations just to give you some semblance of trying to visualize these abstract things I'm talking about. Okay, so neither of these simulations are the best, okay, but it is what it is. So what you're about to see is you're about to basically see lines that represent the electric field surrounding 2 point charges. And we'll talk more about these lines later, but notice if I just have, let's say, a single charged particle, this red one is a charged particle, there's something affecting the space around it. Okay, something invisible, we can't really directly see with our eyes, but this charged particle is creating its own electrical field. Now this gray particle right now has no charge, and so it basically is ignoring this electrical field. But if I charge the second particle, then all of a sudden they start to interact with each other, and you can kind of see, again, these lines represent the electrical fields between these 2 points. And in this case, we get kind of an interesting effect. Notice as I move them towards each other, because they're both positive charges, this is +2 and this is +2, they're both positive charges, the electrical field actually between each particle actually starts to bend. And the reason is, remember, a field is defined by only one single quantity at every point in space, and so you can never have electrical field lines crossing because you can only have one single electric field at any point in space. I don't know that this simulation is going to be any better, but here basically we have 4 point charges, and each of these, you can kind of see these lines are just trying to visually represent the electrical field created by each of these charges. And so each individual charge creates its own electrical field, and then that electrical field, or at least the sum of all of those electrical fields, influences each of the other charges. And so if I move one around, we can see that affects all of the other electrical charges nearby. And again, this is just a visual representation of the idea of the electrical field, that there's some invisible thing that surrounds all charged particles, that permeates all space, that we can't directly detect, but we can indirectly detect it if we were to hypothetically take a test charge out of our pocket and just put it out there. Okay, so I don't think that there's anything really new on this slide. This is the definition of the electrical field. Again, that is the electrical force per unit charge at any point in space. Just some general things about the electrical field. Again, you definitely want to make sure you add this to your notes. The symbol for electrical field strength, I said this before, is a capital E. It is defined as the electrical force per unit charge at that location in space. Definitions are important, so definitely make sure you add that to your notes. In other words, the electrical field, or the electric field at a point in space, is defined by what the electrical force would be on a test charge if you were to put a test charge there. But we talked about the idea that even if I don't actually have a test charge with me, there's still something happening in that space that we can only detect by putting a charge out there. Electrical field is a vector quantity. The unit for electric field strength is newtons per coulomb. That just comes from the equation, of course. Electrical force, any force is measured in newtons, and it's force per unit charge. So if force is in newtons and charge is in coulomb, then the unit for electrical field strength would be newtons per coulomb. And the direction of the electric field vector, the direction of it is always in the direction that a positive charge would feel a force. And that's a very easy sentence to say, but just to clarify, when I say a positive charge means positive charge. That's pretty self-evident. Would is underlined because, again, if I take a charge out of my pocket, I can measure the electrical force on it and divide by the charge to find what the electrical field strength is. If I don't actually have a charge with me, there's still something there. And so that's why it says would. I don't have to have a test charge to know there's an electrical field at every single point in space in the universe. I also underlined a force because one common misconception students have is whichever way the electric field is pointing is the direction that a positive charge would move. And we spent a lot of time in IB Physics 1 talking about just because an object is moving in one direction doesn't necessarily mean that there is a force making it move in that direction. That has to do with, like, Newton's laws of motion and whatnot. But I digress. Let me see if I have any other simulations to share with you, and then we'll do some basic calculation questions. Okay, so this simulation is, again, just a representation of a point charge, a single point charge, and the electrical field it creates around it in space. These arrows are basically showing you the electrical field of the single point charge. If I have something more complicated than a point charge, let's say 2 point charges, we can see they start to interact with each other. Actually, let me show you something that's not going to completely blow your minds. Something like this. And I can have very complicated types of charge distributions. Like I could have, different lines of charge that create really fancy looking electrical fields around them. I could have like a conducting sphere. If you ever take physics in college, you'll deal with more complicated situations than single point charges. You could have like a ring of charge that has its own electrical field, and it can get pretty complicated actually. And just to show you the same thing, this is a single point charge, and basically what I want you to see is that, every single point charge in space creates an electric field surrounding it, whereby if I were to put another point charge just out there, that point charge would feel a force. Okay, so for example, my mouse right now, you can't really see too well, but I can add more complicated charge distributions, and you can see again the electrical field. This is just 2 point charges, 2 positive point charges creating an electrical field. Here we have my simulation has crashed. That's not good. Alright, well, anyway, let's do some basic calculations and finish up this video. Okay, so example 1. An electron is placed in an electric field of strength 200, this is an awkward unit, nanonewtons per coulomb. Calculate the force that acts on this electron. Okay, so remember the way electrical field strength is defined is the electrical field strength at any point in space is defined as the electrical force that a charged particle would feel divided by the magnitude of that charge. Now in this case we're given the electrical field strength. Remember electrical field strength, that's the symbol E, 200 nanocoulomb. That would be 200 times 10 to the negative 9 newtons per coulomb. And if we want the force on this particle, note that it is an electron, and so we know the charge of the electron is negative 1.6 times 10 to the negative 19 coulomb. We talked about this in the last video, but remember this negative sign indicates that it's a negative charge. I don't want you to confuse that with indicating anything about direction for the force that we're about to calculate. I also want to point out, though, that the electrical field strength, by definition, the direction of that vector is whichever way a positive charge would feel a force. And so if you were to place an electron into an electrical field, it would feel a force in the opposite direction of that electrical field. Okay, so I'm doing this calculation now. I'm basically just, basic algebra. I have 200 times 10 to the negative 9 times 1.6 times 10 to the negative 19. And I get a ridiculously small force that is so small it doesn't even matter. But there you go. I don't even know that this is measurable. But that is how you would do this calculation if it made any sense. And again, that's just using the definition of electrical field strength. Okay, so pause there if you need to look at that some more. Okay, example 2. An alpha particle is placed within an electrical field and immediately feels a force of 0.0025 newtons. Calculate the magnitude of the electric field at the location where the alpha particle is placed. Okay, now, number one, if we want to find the electric field, that is defined as the electrical force per unit charge at every point in space. So if we put an alpha particle out there, remember an alpha particle is just a helium nucleus, just 2 protons and 2 neutrons. If we know the force, okay, and we know the charge of the alpha particle is 2e, which is 2 times 1.6 times 10 to the negative 19 coulomb. That would be 3.2 times 10 to the negative 19 coulomb. Then we can calculate the strength of the electric field here. By the way, this number is also going to be ridiculously big, and so don't worry too much about the numbers. I'll try to give you numbers that actually make sense on actual test questions and whatnot. So if you think that this value doesn't look very realistic, you're probably right about that. I guess I need to be more careful making up numbers. But that's how you would do this calculation. Keep in mind that the electrical field that we're calculating here is not the one created by the alpha particle. It is one that already exists by some other means. The alpha particle does have its own electric field, but we're ignoring its own electric field just for the sake of doing this calculation. In other words, what I'm saying is, what if it wasn't an alpha particle? What if it was an electron? Okay, would that change the electric field strength? No. Okay, because if I took an electron out of my pocket instead of an alpha particle, if I put it out there, it would feel a smaller force. Alright, so Fe would be a smaller value. But the charge is also smaller, and the ratio would still be the same. And so whether it's an alpha particle or any other charged particle, I would still find the same electric field strength. It's just that the force, of course, would be different. Okay, so that is example 2. Let's take a look at example 3. Example 3. An electron with a mass of 9.11 times 10 to the negative 31 kilograms enters a uniform electric field of magnitude 1.35. Again, a really awkward unit, I apologize. Millinewton per coulomb with a horizontal velocity as shown to the right. The first question says, state the direction of the electric force which the electron experiences. Now, first of all, I want to remind you, the direction of the electric field shows the direction that a positive charge would feel a force. Not which way it would move necessarily, but which way it would feel a force. The electron does not have a positive charge. And so you can imagine basically the electron doing the exact opposite of what a positive charge would do. Now, as soon as this electron enters this field, notice that the field is pointing down. So the electric field in the situation is directed straight down. That means the direction of the force on the electron, as soon as it enters this region here, is going to be up, in the opposite direction of the electric field. Negative charges feel a force in the opposite direction of the electric field. Now, does that mean the electron is going to move up? Well, yes and no. What's actually going to happen is as soon as the electron comes in here, it's going to feel a force. Okay. In fact, it's going to feel two forces. Number one, it's going to feel an electric force up due to the fact that it's in an electric field. And of course, there's also a force of gravity down. Alright, now the second question says, determine the magnitude of the electric force acting on the electron. We can do that very easily just using the definition of the electric field. Like so. That electric force would be Q times E. The electron has a charge of negative 1.6 times 10 to the negative 19, just to save space on the screen. I'm not going to write that out. But of course, the charge of the electron we know is negative 1.6 times 10 to the negative 19. And the electric field strength here is 1.35 times 10 to the negative 3. Okay, it's 10 to the negative 3 because milli is 10 to the negative 3. Maybe I should write that out actually. So 1.35 times 10 to the negative 3. And again, this number might seem very small, and it is like ridiculously small. I apologize for that. Now again, I caution you not to obsess too much about this negative sign, because the negative sign was on the charge, which is a scalar. Now we just calculate electric force, which is a vector. Okay, what does this negative sign indicate? Does that mean that the force is down? No, of course the force is going to be going up. We just established that. So in other words, this negative sign here really does nothing for us at all. And so again, don't obsess too much about negative signs in this unit. Okay, just pay attention to which way the force or which way the field is actually pointing. Okay, now the last question says determine the acceleration of the electron in this field. And for this question, we are going to go back to our old buddy Newton's second law, F net equals ma. And I'm going to write out my second law equation. If I write down the sum of the forces, I have the electric force going up, and I have the gravitational force going down, and that's equal to m times a. And I actually know what the mass is, because it's given in the problem. And I just calculate Fe. I can easily find Fg using my good old force of gravity equation. So that would be negative 9.11 times 10 to the negative 30 newtons. And by the way, if you compare this 10 to the negative 30 to 10 to the negative 22, Fe dominates force of gravity. Force of gravity doesn't even matter in this calculation. I might as well just leave it out because it's like, 8 orders of magnitude smaller than the force of gravity. Okay, and so to find the acceleration, I don't really care about Fg. It does nothing for me in this calculation. Normally I would include it, but it's not going to change any of the answers here. Okay, so I can find the acceleration just by dividing by the mass. And so that would be 2.2 times 10 to the negative 22 divided by 9.11 times 10 to the negative 31. And I can calculate the acceleration like that. And I'm not gonna finish that calculation because I think that's something you can do on your own, and I want to finish this video. I do want to point something out though, just really quickly. If you were to do this experiment in real life and you were to measure where the electrons are actually doing once they enter the electric field, basically what's going to happen is the electron is going to come up into this electric field, and it's going to experience a constant acceleration. Okay, the acceleration is going to be constant because the electric field strength is constant in this situation, which means the force is going to be constant, which means the acceleration is going to be constant. And if you have an object moving horizontally in a constant acceleration situation, you have something that we spent some time talking about last year, which is basically a projectile motion problem. Okay, and so this electron is actually going to move in a parabolic arc. Okay, kind of like how if you threw a ball off a table, it would move in a parabola, only this parabola is going up instead of down. Okay, but this is essentially a projectile motion problem, and you could conceivably see a projectile motion problem masquerading as a electric force and electric field problem. Okay, so I'm not saying that's necessarily going to happen, but it could definitely happen. The IB loves to combine multiple topics like that, and so it wouldn't surprise me at all to see this type of situation where you had a charged particle and an electric field, and you had to also take into account things like horizontal displacement and how long does it take to fall, and stuff like that. Okay, so just something to be on the lookout for. Okay, so I'm going to go ahead and stop this video here. As always, please let me know if you have any questions, and I'll see you guys in the next video.